All right, today we're going to talk about something really cool. It's a tool, a way of thinking, really, that scientists and engineers use to solve problems that seem, well, completely impossible. We're going to learn how to map these invisible worlds of possibility, turning total chaos into a chart we can actually navigate.
I mean, seriously, how do you even start with a problem like that? So many of the biggest challenges we face, whether it's in AI, logistics, or even quantum computing, they all involve finding that one perfect answer in a sea of options so vast it's hard to even imagine. When just guessing your way through isn't an option, you don't need a faster computer, you need a better map.
So the first step is to completely change how we see the problem. Instead of thinking about a list of answers, I want you to imagine a huge, invisible landscape. In this landscape, every single possible outcome, every arrangement, exists as a point. And our goal? It's to find the lowest points, the deep valleys, because those represent the best possible solutions.
Okay, so to even start building our map of this landscape, we first have to define what a point on that map even is. Each one of these points is called a configuration. Think of it as a complete, unique snapshot of the system at one single moment in time.
Now, this collection of every single possible configuration has a formal name, the configuration space. You can think of it as the ultimate atlas for any problem. It literally contains every state the system could ever possibly be in, the good ones, the bad ones, and everything in between.
And this right here, this is a perfect picture of what that landscape looks like. This is for a math problem, but you can see it, right? The lighter areas, the high mountains, those are terrible solutions. But the darker, lower areas, those four distinct ovals you see, those are the valleys. They're the sweet spots, the optimal solutions we are desperately trying to find.
You know, the idea of a configuration isn't as abstract as it sounds. For a tiny particle, it's just its x, y, z coordinates. For something like a satellite, it's not just where it is, but also which way it's pointing. And for a complex robotic arm, a single configuration is the precise angle of every single one of its joints. Each of those is just one point in a much, much larger configuration space. So, great, we have a map of all possible states. But here's the catch. This map is usually way too big to be useful by itself. What we really need to know is how we can get from one state to another. We need to chart the valid paths. And when I say too big, I'm really not kidding. There's a classic AI problem called the blocks world. If you're just arranging 10 blocks, you get over 58 million unique configurations. Bump that up to 18 blocks, and the number skyrockets to over 588 quintillion. You just can't wander around a landscape like that hoping to get lucky. This is where things get really clever. We have to simplify. So we create what's called a transition system, or a transition graph. And here, we stop trying to look at the entire landscape all at once. Instead, we just focus on the valid states and the allowed moves, the transitions, that can happen between them. The idea is just so elegant and simple. Every configuration becomes a dot, a node, on our graph. And if you can legally move from one configuration to another, you just draw a line, an edge, connecting them. Instantly, the problem changes. You're not exploring an infinite landscape anymore. You're just navigating a network. Now that we have a map with clearly defined paths, we can use it to do something incredible. We can efficiently find the best possible solutions, those lowest valleys from our landscape. I mean, in any optimization problem, the whole point is to find the configuration with the lowest cost or the lowest energy, right? On our landscape, that means finding the bottom of the deepest valley. On our new graph, it's a very specific kind of node that we can now hunt for with an algorithm. Let's look at our landscape again. See those four deep valleys? Scientists call them local optima, basically solutions that are better than anything right around them. And since these four happen to be equally good, they're also the global optimas. Our transition graph gives us a map of the easy, low-elevation paths between these valleys, so we don't have to waste time climbing over those massive mountains to find all of them. And we can even take this one step further. There's a technique called a local optima network, or LON, that creates an even more compressed map. It's kind of like a subway map of a city, right? It doesn't show you every single street. It just shows the stations and the lines connecting them. A LON does the same thing for our problem. It only maps the best spots, the valleys, and the direct paths between them. It's a massive shortcut. What's absolutely incredible is just how universal this idea is. This method of mapping states and transitions isn't just for some abstract math problem. It's being used to understand wildly different systems in the real world. Just look at these two images. On the left, you're seeing how thousands of physical disks can shift around to become unjammed.
The arrows are showing valid transitions in that system's configuration space. On the right, that's a graph mapping the states of qubits in a quantum computer. One is a physical, classical system you could touch. The other is quantum. But the fundamental problem-solving approach is identical. Define your states, map the valid moves between them, and find the best path. It's the same idea, applied at completely different scales of reality.
And the applications are everywhere. This exact way of thinking is what's behind how a robotic arm plans its path, how an AI solves a complex puzzle, how logistics software finds the best delivery route. It even helps physicists understand how proteins fold. It's a fundamental way of making sense of complex, constrained systems.
So, what's the big takeaway from all of this? What's the main idea? It all comes down to the profound power of abstraction, the power of creating the right kind of map. And this right here is the magic trick. By changing our whole perspective, by going from an impossibly vast landscape to a well-defined network of dots and lines, we transform problems that seem completely unsolvable into structured puzzles that our algorithms can actually navigate and ultimately solve. You know, the researchers who work on this stuff put it perfectly. This network view lets us see relationships that were completely invisible before. We can literally see the hidden connections between good solutions and understand the structure of the problem in a way that just staring at the raw data would never allow. It reveals the hidden architecture of complexity itself. This leaves us with a pretty fascinating final thought. This method of mapping configuration spaces gives us an incredibly powerful lens to look at the world. From the quantum realm all the way up to global logistics, we are learning to chart the invisible. The only question is, what vast landscape of possibilities will we map next?